Good morning, everyone. This is Open Fabrics Alliance 2020 annual workshop in a new format. We are trying for the first time the virtual format because of the current situation with COVID-19. The 2021 workshop has already been set. It is in March 21st. I believe the information is on the website. If you want to already start planning for your 2021 workshop, please feel free to do so. Doing the workshop virtually has its own advantages and disadvantages. Of course, there is no travel required, but unfortunately, there is no real-time interaction. We will try to keep this virtual workshop as interesting as possible. There is Q&A box in your WebEx window on the bottom right corner if you would like to submit a question to the presenter. I request the presenters to complete their presentations in 25 minutes and leave 5 minutes for Q&A. I will be moderating the questions. Rashika, to begin with, first with you. And this is a new format, so we are also trying a new agenda. Every day, we will be meeting between 8 a.m. and 11 a.m. this week. There will be sessions, and there is a bird of feathers topic as well. The sessions are all pre-recorded. The sessions are all recorded. In other words, it will be available on the YouTube channel of OFA as soon as the recordings are available to the host. The presentations, the actual PDF files will also be available by the end of the day or the day of presentation. There is also a survey every day, and the link will be sent to you by our press at openfabrics.org. Please, I request you to submit the survey so we know how we are doing. This is a new format. We would like to hear from you. And there is also a general survey about the workshop that will be given to you end of the week, which is on Friday. And the agenda today is there are about 5 presentations with a break in between 9:30 and 10 a.m. So with that, I want to welcome our first presenter, Rashika. Rashika works for Amazon. She is a senior engineer at Amazon Web Services, where she has been working on providing performant and high scalable networking and storage solutions to EC2 customers. She's been focused on enabling customers in the past, and she has run large-scale machine learning applications in a performant way. In the past, she has also worked on developing and providing Amazon Linux kernel and hypervisor to millions of customers and contributing patches to the Linux kernel, where she was the fourth most active developer in 2014. So I'm excited to have Rashika speak about Libfabrics and the use cases, learnings, best practices from her experiences. Rashika, please feel free to take it away.
Thanks, Divya, for the introduction. Hello, everyone. Good morning. I'm Rashika, and I'm super excited to talk to you about using Libfabric for scalable distributed machine learning. My primary work at Amazon Web Services has been to enable customers to run machine learning workloads using EFA on EC2. And as a part of that, I get to work with a variety of large AWS customers, and I thought I would share the learnings I have seen from working day in and day out with the machine learning workloads. Next slide, please. So before we get started, I want to encourage you to write down any questions that you might have throughout the presentation. I plan to spend around 25 minutes for the presentation, and we'll take questions after that. In case we're not able to cover all the questions, please feel free to reach out to me via email, and the email address is mentioned at the end of the presentation. To quickly describe what we'll cover in the next 30 minutes, we'll start off with an overview of what distributed machine learning training is and what software components constitute them to run it efficiently. We'll dive deeper into the networking pieces of the stack, including Nickel, Libfabric, and EFA. And then we'll discuss how this compares with the performance benefit over the traditional TCP stack. We'll conclude by discussing some learnings we have had while running this software stack at scale. Next slide. So I want to spend some time, just the slide before this. So I want to spend some time to emphasize how machine learning training differs from typical high performance computing applications. So let's try and cover that. Next slide, please. So the most common method of machine learning training is supervised machine learning, where you train a model based on labeled examples to calculate what are the optimal values of the weights and biases are. And then you take this model and apply this on real world examples to infer results. So for example, if you want to develop a machine learning model which can identify between cats and dogs images, you would have to train the model against labeled examples of cats and dogs of different breeds, sizes, colors. And then after the training completes, you can use the resultant model and let it identify whether the given image is a cat or a dog. And one of the interesting things about machine learning models is that it is growing way faster than Moore's law. What it means is that the size of the machine learning model would grow more than double in the next 2 years. As an example, BERT, which is a very popular natural language processing model, currently takes millions of parameters for training, and it takes around 9 days to train it on a single biggest server available. But no one wants to wait for 9 days to get results, right? Ideally, we would want it in the order of magnitude of R, because minutes would be an unrealistic expectation. This is achieved by running the supervised machine learning training in a distributed manner by using data parallelism. So in data parallelism, you deploy the training models on all computing resources and train them in parallel using different data sets. In the rest of the presentation, we'll focus on distributed machine learning models which employ data parallelism. Next slide. So in data parallelism, machine learning models uses an algorithm called as stochastic gradient descent algorithm for calculating the optimal parameters for training. It is a very popular algorithm which uses an iterative method to find out the optimal parameters. In each round, you are training the model in parallel on all the computing resources, GPUs in our flowchart, and collect the resultant variation from all the GPUs before updating the model. So if you look closely at the flowchart, each of the GPU resources, which are marked in the blue boxes, have the training model, and they train against their respective mini batches marked in the purple boxes. Because each device is training on a different sample, it computes different local gradients to the model. And what local gradients are, they are basically the errors between its prediction for its training samples and the labeled output. The GPU then sends these local gradients to other GPUs in the cluster and wait for the gradients from all the other GPUs. After the network communication finishes, the model is updated and sent to all the GPUs before the next round begins. So as you can notice, the sending, waiting, and receiving for the gradients is a very network intensive step. Now let's see how we deal with this typically in real life deployments. Next slide. So we want the performance of our training model, which is measured popularly in terms of training time, to scale linearly with the number of GPU servers. But in reality, that does not happen. This is because you throw in more GPUs, you're computing more in each epoch. You can think of epoch as a unit of time, because more GPUs can process more data at the same time. And after each epoch gets over, you update the model based on large amount of data set, which means that you're updating the model less frequently. This can lead to a slower convergence time because you're updating the model after training on large amounts of data. Whereas in the other case, where you train the model on less number of GPUs, keeping the compute per epoch shorter, you update the model much more frequently, letting the model converge faster, but you instead increase the amount of network communication which can happen per compute. So to solve this chicken and egg problem, we would want to have a faster and lower latency interconnect that can either allow us to scale while maintaining shorter epochs, to converge faster for same number of nodes, and that is the problem we have tried to solve with the low latency interconnect networking stack. Next slide. So in the next section, we'll discuss this entire software stack, which goes into making an ML training highly performant. Next slide. At the top of the stack, so here is a wholesome diagram of what machine learning training architecture looks at AWS. It is very similar in any other environment system as well. So at the top of the stack are different machine learning training models like BERT and Transformer, which is used for natural language processing, MASKRCNN, which is used for object detection and segmentation, and Jasper, which is popular for speech recognition. This is just a handful of the machine learning training models available. There are multitudes of it for various kind of purposes. So these models use different machine learning frameworks like TensorFlow, PyTorch, MXNet, Caffe, and more, which supports distributed training across multi-node and multi-compute resources cluster. So one of the common backends these machine learning frameworks use for multi-GPU, multi-node communication is NCCL. NCCL implements different collective communication primitives, which relies on network capabilities of the underlying network stack. Here in this architecture model, we are using Libfabric as the networking stack. AWS developed a plugin called as AWS OFA NCCL, which allows NCCL-based applications to use Libfabric. What it means is that on EC2, the machine learning folks can use EFA provider of the Libfabric for network communication. So all of these software components can run on AWS EC2 infrastructure, which provides virtual machines on demand. And these are elastically scalable, which means you pay for as long as you use them. Next slide. So in the next part of the talk, I'll be describing the networking pieces of the stack, starting from the NCCL to EFA. Next slide. NCCL is multi-GPU and multi-node collective communication primitives. It provides various kind of collective routines like as all gather, all reduce, broadcast, and these are used as a foundation of the implementation of the collective operations that NCCL does for network. And this is highly performance optimized for NVIDIA GPUs. NCCL does this efficient communication by probing for, by finding the system topology. For example, probing for available GPUs and NICs, identifying distance between them to form a collective operations topology like ring or tree-based communication. And it then schedules the CUDA kernels, which are responsible for reducing the data and moving it around. So NCCL used to support sockets and InfiniBand verbs for communication before AWS developed the open source plugin called AWS OFA NCCL. This plugin acts as a layer between the NCCL and implements all the network APIs of the NCCL using the Libfabric API. And that is how it allows to use the Libfabric as a networking stack. On EC2, it allows to use EFA. The motivation of why we would want to use EFA is covered in the next slide. So next slide. So EFA is a Libfabric provider, which is optimized for HPC and ML workloads. It provides low latency for internode communication by bypassing the operating system. We have built to allow it to scale to thousands of CPUs and GPUs. And it does that by using a custom protocol called a Scalable Reliable Datagram, which has been specifically designed for AWS data centers. It is a very interesting technology which uses multipath routing by spraying packets over multiple paths to avoid hotspots and has inbuilt congestion control for large cloud systems. To learn more about EFA, you can browse the link on the slide or join our discussion in OFA 2020 about EFA on Friday at 10 a.m. Next slide. At this point, I'll take a pause from the information overload and show some performance numbers, which will hopefully justify the time we have spent in understanding all these components. Next slide. So we ran training benchmarks for two popular machine learning models. One is the BERT model, which, as I mentioned before, is used for natural language processing. So the output of the BERT model is a pre-training model, which can be fine-tuned to service a variety of NLP tasks like question answering, language modeling, etc. To train this model, we used a data set provided by NVIDIA, which is a concatenation of Wikipedia and book corpus. And we applied certain optimizations to achieve better performance. So one of the optimizations we applied was gradient accumulation, which basically means that you train the model on mini batches, but aggregate the gradients for a certain number of iterations before you send it over the network. What this helps us is this simulates a large batch size and speeds up the training. We also use smaller sequence length for the same reason. We found that we could achieve 87% scaling efficiency when scaling from a single server consisting of 8 GPUs to a cluster, which is consisting of 2048 GPUs. And the training time reduced significantly from 9 days to less than an hour. In the other benchmark, we trained MASKRCNN with COCO dataset. We configured model hyperparameters like learning rate, batch size, and more for clusters of different sizes to achieve optimal performance. And we found out that EFA outperformed TCP for all cluster sizes, and it could process more than 1,000 images per second with 192 GPUs. Next slide. So in the next two slides, we are going to pictorially represent the information that I just shared in the last slide in more details. So here, the first slide consists of training time improvement with the BERT model. So on the x-axis, we have mapped the clusters, the different size of the clusters in terms of number of GPUs used. And on the y-axis, we are mapping the training time. So any software stack which is going to lead to a lower training time yields better performance. On the blue boxes here, we have mapped the training time of the model with EFA software stack. And on the orange boxes here, we're mapping the training with the traditional TCP software stack. So as you can see, for a cluster of size which consists of 8 GPUs, which is basically a single server for us, the training time is equivalent for both EFA and traditional TCP stack. And this is because the network is not utilized at all. And as you scale up the cluster to move to a multi-node system, you can see that EFA is performing, has a reduced training time as compared to TCP. And if you see closely at the 256 number, with 256 number of GPUs, the performance is double, which is like the training time is reduced to half when using a Libfabric provider. And for the cluster of size 2048, the training time has reduced to less than an hour, which basically means you can go for a lunch, come back, and your training is done. Next slide. Here is a second graph, which maps the performance improvement in MASKRCNN using the COCO dataset. On the x-axis, similar to the previous one, we have mapped the cluster sizes consisting of number of GPUs. And on the y-axis, we are mapping the images processed per second by the training model. So more number of images that you process per second yields higher performance. In the orange boxes, we are mapping the performance number with the TCP software stack, and with the gray, we are using EFA. So as you scale up the cluster here, you can process more images per second with EFA. So for example, at 16, we can process 30 more images per second. And at 192 GPUs, the difference becomes 170 more images per second. So that means in a period of, let's say, 2 hours, we would be able to process more than 1.2 million images with EFA as compared to with TCP. Next slide. So all these performance comparisons with the traditional TCP stack looked promising, but we realized that this is not the complete story when we started deploying these models at scale. We faced new challenges, and in the next couple of slides, I would like to describe these challenges and some possible remediations that worked for us. Next slide. So one of the things I like about my job is I get to work with a diverse group of customers who are running complex ML training workloads using our technology. They are using different ML frameworks and have different cluster sizes. So in all, they are very unique in each of the cases. They want to run these demanding workloads on our P3DN servers, which are optimized for machine learning training at scale. And about P3DNs, these are very complex servers with 8 Volta 100 GPUs. It requires high frequency and power draw. It uses EFA for networking, and it's an integration of multiple complicated hardware components. So what customers want is to run these workloads reliably and get consistent performance. To achieve this goal, we have to do intensive qualification and testing of all the software stacks, ranging from the firmware controlling the hardware to the virtualized instance stack, including NVIDIA drivers, Libfabric, Nickel, ML framework, and so forth. We also need to ensure that the underlying hardware is reliable and can auto recover in case of transient failures, which are very likely to happen for these demanding applications. On top of ensuring that we have enough testing and validation of both software and the hardware, it's still important to cover a few other aspects of deploying at scale, which we'll talk more about in the next slide. Next slide. So the first and the foremost is to ensure that you know your software stack. As we have discussed before, there are multiple software components involved to make ML training possible and performance efficient. This makes our stack very powerful, but also there is a chance for bugs to exist. The good thing is that each of these communities are constantly fixing bugs and introducing new features. This is why it's important to ensure that you don't lock yourself to a specific version and update the software frequently to get those advantages. So for our case, it would mean updating the NVIDIA toolkit, OS distribution, Libfabric, Nickel, and others. I'll share a customer story that made us realize that knowing the software stack is important. We had an experience with one of our customers who developed their ML stack using an older version of NVIDIA driver. Everything was working fine at the POC stage, but as soon as they started scaling up their clusters, their training used to hang intermittently. This issue was because some GPUs on the cluster would enter a hang state due to a race interaction between their workload and power management functionality. We debugged this issue with them and identified that this is a known driver bug, which has been fixed in later versions. So after they upgraded the cluster with new driver installation, we could let the training run uninterrupted. The second important learning is these ML training workloads are very demanding applications and require high performance of each of the resources involved in training, which constitutes network, storage, and others. This is why it's important to carefully examine and identify any possible bottlenecks that can reduce performance. An instance of this was seen when we were debugging a crash, training crash that happened like within minutes of training getting started. It threw a framework error, which indicated that there were issues loading the data from the file system. And after we profiled all the resources involved, we analyzed that the storage system wasn't efficient enough to meet the training standards of the customer. So therefore, we asked the customers to move from using an NFS-based storage to local SSDs through which they could run the training for hours. This solution works for a smaller cluster, but when you move to large cluster, you would require a high performant distributed file system like Amazon FSx for Lustre. We also have EFA for efficient networking, along with powerful servers like P3DN designed for ML training at scale. The last but definitely not the least important is to design the system which is fault tolerant. Since these systems have lots of moving components, the probability of failure increases. This is why we need to enable mechanisms that can let us recover from these failures graciously. Some of the examples include taking periodic snapshots and restart from a known good snapshot if the training dies. AWS provides parallel cluster with Slurm, which can help in this aspect. Slurm is a technology which allows you to schedule jobs on the cluster, and it monitors all the nodes for its health. So if it detects that there is any node which dies, it automatically removes it and introduces a new node as a replacement. Another aspect of it is to be proactive and continuously monitor your system, whether it's hardware or software, before failure happens. One example of this is to look out for any possible GPU errors like memory corruption errors and identifying the GPUs which can potentially go bad in future and removing them from the training cluster before the performance reduces. At AWS, we monitor hardware components on customers' behalf, but we still rely on them to monitor which goes inside their VM. One important thing I've learned is that these issues actually seem like small inconveniences at small scale, but with large GPU clusters, it magnifies to have a significant impact. Next slide.
Rashika, we have some good questions. I want to make sure there is at least 5 minutes to answer those. So let me know when it is time to bring it up.
Sure, I'll let you know. So I'm just at the summary slides, so it should be quite quick. So to summarize, the ML training models are growing at an extremely fast pace. So to make sure that they run in a reasonable amount of time, it is crucial to lower latency. It is crucial to have a lower latency interconnect for fast distributed machine learning training performance. EFA and other Libfabric providers help in achieving the goal by bypassing the operating system, among other things. We also saw that the stack shows orders of magnitude improvement against the traditional TCP stack. And lastly, when deploying these applications at scale, we should make sure that we size the hardware carefully, make sure we're using the latest versions of all softwares, and be better prepared for failure cases. Next slide. So that's all what I had to cover in this presentation. If you have any ML trainings to run, spin up a P3DN instance, choose a training model, and get started. You can enable EFA at no additional charge for supported EC2 instance types. And I will be taking the questions that we have now.
Okay. Thank you, Rashika. That was a great discussion. So you have two categories of questions. One is a more generic one, and then on page 17 and 18. So I'll cover the generic one first. The question is, does the ML application mainly use the all-reduce collective algorithm?
Yes, that is correct. So most of the most of the collective operations are using all-reduce collective algorithm. But what I have observed is that even with all-reduce, the implementation varies. But talking about Nickel specifically, it is totally all-reduce based.
Okay. Second question, does EFA or AWS EFA and CLL use GPU direct, and what type?
So it does not use GPU direct right now for production use cases.
I see. Okay, good. And more on performance, the slide that is being shown right now, 17 and 18, the one after that as well. What percentage of the total time is communication?
Okay, so as I mentioned in the BERT model, we are using something called as gradient accumulation. So this is amount of communication you want to have is something that you can tune while you're training the models. So in my specific case, when I was getting these numbers, I was using for every 64 iterations, the 64th iteration was leading to a network communication, and it takes about, let's say, 2,000 steps to get it over. So I would say roughly around 20 to 25% is definitely network.
I see. Okay. Follow-up question. The improvements here seem to be rather incremental. What is the real advantage of EFA here? Latency, CPU, or bandwidth?
The advantage of EFA is latency and bandwidth both.
Okay. And I think it's in the follow-on slides. How many network adapters and at what speed per 8 GPU server is the question. It is when you were talking about the epoch setup, I believe.
Okay, so the server have one network adapter and it runs at 100 gigabits per second.
Okay, thank you. How much data is exchanged once every epoch? How does it scale with the number of nodes?
So with the okay, I don't remember the exact numbers for how much data is exchanged between the nodes, but in my example, I was using a smaller mini batch size to have less communication. But when you move up, I ensure that the overall the communication size remains the same. So I wasn't playing around with the sizes much, but I can get back with more specific numbers to whoever the question is for.
Okay, yep, you can send it to me and I'll forward it on to the
Yes.
Person asking. Is there a performance comparison with RDMA capable NICs with full offload versus software TCP/IP?
No, I don't have those numbers at hand with me right now. I can come back to this question as well.
Okay. What is the underlying network type? Ethernet, InfiniBand, or something else?
It's not InfiniBand exactly. It is a custom software stack that we have developed at AWS using the SRD, the Scalable Reliable Datagram Protocol, as mentioned in the slide talking about EFA. It's not TCP as well because it varies very differently from how TCP is implemented, which is relies on connected establishment, whereas SRD is ensures reliability but does not require connection. And in InfiniBand, you require connection, and it is a lossless fabric. So there are various comparisons. All of this data is present online, and I can point to the resources which talks more about it.
Good, thank you. I have the last question here, actually two more. That's about the time we have today. The question is, in your results, your number of GPUs use all the GPU cores?
Yes, they're using all GPU cores.
And how does the CPU, not the GPU, utilization compare between TCP and EFA?
That's a good question. So in the case of TCP, the CPU utilization is more as compared to what is being used in the EFA because it's a application intensive when you're using because you're more at the user space level trying to transfer more information, but I don't have the exact numbers to back my data.
Okay. All right, that's about the questions I had for you, Rashika. It's a great discussion and it's very interesting. Thank you for your time today.
Thank you.